We're going to sit here and we're going to wait for it. Wait for it. Almost. Almost. The last minute is always the longest minute. And the last 30 seconds is even longer. Yeah. Da-da-da. Almost. Ah, there we go. Yay. Yay. Well, welcome, everybody. Welcome to another in a long list of live streams of Astronomy Daily Live. So welcome, everybody. Hope everybody's doing well out there. Everything's good here. Nothing too exciting. Nothing too extraordinary. Yeah, things are pretty good. It's actually clear here. It's actually clear, but it's yeah, the moon is out. The moon is out, and it's making the sky really bright. So, you know, my little investigation into seeing if I can observe UV SETI, it's going to have to wait until there isn't any moon around, because it's a 13th magnitude star. It's like there is absolutely no way with almost a full moon out that I'm going to see any 13th magnitude star. No way. No way at all. So, well, welcome everybody. I see that Tom is in the panel. Hey there, Tom.
Hey, Cosmic. How you doing? Sorry I'm late tonight, but...
No worries. No worries. You will just be severely penalized, but we'll take care of that later.
So you're going to dock my panel paycheck?
Well, we're going to have to do something, you know, because time marches on. So
that's true. That's true.
And Bobby's in the panel, sort of a new Bobby. Hey,
I just want to let you know that the reorganization is complete, and I don't have to rely on my bed. I could just have a chair or something. And I can just sit back, relax, and just enjoy the stream.
You have entered the modern era, like sitting on a chair. That's just astonishing. Yeah, that's like revolutionary. Absolutely. So cool. Well, welcome everybody. Welcome in to this live stream where we sit around for an hour or so and just casually chit-chat about all things astronomical, all kinds of astronomy stuff. You know, always things going on, and not necessarily limited to astronomy, right? You know, we talk about space travel and rockets and sci-fi, and we talk about shortwave occasionally, and you know, just all awesome things. You know, we've sort of, you know, turned off the TV and you know, forgotten about the news. I'm being attacked here by this furball. She is relentless. Absolutely. So yeah, and just, you know, sitting around in sort of you know, like a virtual porch with our consumables of choice. I have the dihydrogen monoxide tonight, the H2O. This is you know, for me it's a Friday night, so, you know, go a little wild, you know, with the drinks. Why not? So cheers.
Cosmic getting crazy on a Friday.
It's, you know, sometimes you just got to do it, right? Sometimes you just have to just like, yep, got to do it. So yeah, everything is good here. I got, and I'm going to pull up the chat here before I forget, making sure everything's going good in the chat. So yeah, Uncle Bill over on my Discord server had posted two things about being an astronomer, and yeah, that 5-pager, pretty interesting. You know, that's the that's sort of the typical route for professional astronomers is sort of the academic route, but it's an absolute fact that there are many paths and many sort of landing spots. So you know, read that article for sure. You know, I mean, it's a good read, and it sort of gives you a good idea. But you know, there were a couple of things that sort of made me decide to sort of go a different route, right? And one of those things was that you know, I sort of paid attention and watched what the PhDs did, right? And what I observed, and I think I've mentioned this several times here on this live stream, what I observed is that the professional astronomers, right, spent at least half of their time, probably more like 75% of their time, writing proposals for money. Right? They were almost constantly, you know, worrying about funding, right? And how to get the funding in order to do the work that they wanted to do, which they sort of rarely actually did, right? They would sort of oversee projects to a certain extent, but their main job, right? What took most of their time, and I'm sure now still, is writing grant proposals, you know, to the National Science Foundation, to you know, Department of Defense, Department of Energy, trying to think of other funding sources. Yeah, you know, those are sort of the big ones, at least in the United States here. And I looked at that, and I'm like, dang, I want to do astronomy. I don't want to spend most of my time, you know, and you know, this is sort of putting it lightly, but you know, begging for money. Now they're not exactly begging, and you know, I understand that, but that's sort of what it comes down to. Is that you know, they are competing. There's this pool, right? There's this pool that's you know, filled with dollars, and what most professional astronomers do is they try to get a little bit of that, right? The people that actually do the work are well, the postdocs to a certain extent, grad students, and of course the undergraduates. Those three populations, and I would say, you know, sort of the support staff, right? The programmers, the engineers, you know, they do a lot of the dirty work too. But the professional astronomers, you know, it's sad to say, for the most part, they really didn't do a lot of astronomy, right? they had done a lot of astronomy, right? When they were students and when they were postdocs, that's sort of when they did their work, sort of made their names, right? Created their reputations, and now, you know, being a professional astronomer, uh, they manage and they write grant proposals, and that's about it. And I looked at that, and it's like, yeah, no, I want to be doing astronomy, right? I mean, I want to be doing research. I want to be, thinking about, the kind of work I want to do. I want to write the papers. I want to, discuss all kinds of astronomical things. I don't necessarily want to have to worry about, taking a lot of time, writing proposals, even going to conferences, right? I mean, it just takes a lot of time. It takes a lot of time away from actual work. And my interest is the work. So yeah, so like I said, those, that's a good read for sort of the standard, I guess, well-trodden path, well-trodden path. But realize that there are many paths and many sort of landing spots, and I think anybody who wants to can be a professional anything, right? It just takes the time, it takes the work, it takes the passion, yeah, and that's it. Even if you're part time, what's that?
Takes heart.
Heart, absolutely. And I mean, at this point, I sort of consider myself a part-time professional astronomer. Definitely not doing this full time. Would I want to do it full time? Yeah. I think if there was an opportunity to do, the kinds of research that I want to do full time, yeah, get the bills paid. That's all I care about. I noticed that the what did it say? Is it the median? Let's see. I'm going to cheat here really quick and look at something that you're not going to be able to see. Yeah, the median pay for a professional astronomer in 2017 was $117,220 a year. And yeah, I mean, personally, I really don't know. I don't know what I would do with all of that. I guess it would just be instrumentation and stuff, because I certainly don't need that much. And yeah, I don't really want that kind of those kinds of numbers. That's I don't know what to do with that. But if I could use that, for cool instrumentation and that kind of stuff, sure. But yeah, that's a pretty hefty salary there. So pretty good, if you can do it. But yeah, that was my only point. Go ahead and read that thing, but just realize that is one path, and I've learned that you sort of have to try to follow your own path. Take in these kinds of suggestions, but if it doesn't work, it doesn't work. That doesn't mean that you're not going to be able to do what you want to do. It's just you're going to have to do things differently. That's all. That's all. No big deal. So cheers to doing things differently.
Yep.
And you know, I think too. I mean, one of the things that science in general, I think, really needs is sort of, oh, this is sort of a terrible term, you know, but sort of the unchained scientist. You know, the one who is doing things in the garage, right? Is doing experiments in the garage and in the basement, and you know, driving down the road, thinking about, it's like, huh, I wonder, you know, what would happen if I did this? You know, thinking about doing experiments and thinking about nature, and thinking about you know, how you know, things in the universe work, and you know, how can I experiment with that and learn more? And you know, honestly, you know, if you're stuck at some kind of institution, you're going to be doing the institution's work. You're not necessarily going to be doing your work. So, you know, the independent scientist really needs to come back somehow. You know, these mad scientists who you know, are doing all kinds of you know, crazy experiments. You know, and that's not to say at all that, you know, the work being done at universities and labs and everything else, it is mind blowing, right? It's absolutely incredible stuff, new stuff, amazing. But it sort of has a different flavor, right, than your garage scientist, right? You know, or a scientist, you know, who has a little telescope like that, you know, trying to answer, you know, some kind of question, right? So yeah, lots and lots of different paths, lots and lots of different ways to sort of land yourself as a professional or semi-professional scientist. So yeah, don't think that there's only one way, because there isn't. You know, there's a well-trodden path that most people go down, and I don't know. You know, I mean, it comes down to sort of a personality thing too. And you know, whatever floats your boat is perfectly fine. And you know, professional astronomers who follow sort of the standard path. I mean, it's obvious, right, that these folks are just doing amazing work. I mean, we read these papers here all the time. It's just absolutely incredible, the amount of time and effort and you know, thinking that has to go on, you know, to do this kind of work. So yeah, I'm not really knocking anybody at all, because I think it's all awesome. Just realize that there's a lot of paths, not just that one that's written down in that little brochure. So cheers to multiple paths. I got some coffee here, by the way. All right, well, cool. Hey, there's a I think there's a rocket launch pretty soon. Maybe in the next hour or so.
No,
right?
I believe it went off already.
Okay.
It was scheduled for 9:45 Eastern. So, I took a little look, and what I saw on the web was it was successfully launched. So
cool.
It's going okay, yeah.
Cool, nice. They were they going out of down south, right?
I think it was from Kennedy Space Center. Yeah.
Or was it? Oh, okay, okay.
I think, I'm not sure, to be
Yeah.
honest with you.
I thought that this was one of the ones that was down in South America.
You might be right. This might be an ESA.
Yeah, I don't remember exactly. I think
Yeah.
it was an Ariane 5, though, right? So
Yeah, if it's Ariane 5, then it was from ESA's launch site. Yeah.
yeah. So,
Yeah.
but from what you've
And right
heard,
now, I think you can watch the launch on demand. I might do that after this show. And I
yeah,
might want to put my table like this way after the show, so maybe I might have like some. I like when I first got the antenna, the long wire. I actually had it like long enough so it could be like so I can use it for like my Texan radio. And then I got the RTL SDR, and I have been using the long wire with my SDRs ever since. So so what I'm trying to do right now after the show is like push the table back to like right here by the TV and see how much better it is stuff.
cool. Do you do you usually have the antenna up in that room, or do you have it outside, Bobby?
It's outside. I also got it like vertically polarized,
Uh-huh.
so it's usually great.
Sweet. Nice. Well, you know,
Then I
oh.
use the teleweb for BHF UHF purposes.
Cool. What was that, Tom? Go ahead.
Yeah, I was just going to say, you're right. The Bepi Colombo launched from French Guiana on an Ariane 5. Everything seems to be going well right now. So
Nice. Yeah, I think those are pretty reliable rockets. I don't. Yeah, I don't know if. I mean, they probably have had some kind of mishaps, but I'm not recalling any. Yeah. Well, good. Yeah, I was talking to somebody today about Elon Musk's plans to launch like 12,000 satellites for the high-speed gigabit network stuff, and yeah, you know, I still, you know, I'm thinking that that's a that is going to be sort of a problem for ground-based astronomy, because you know that's effectively doubling the number of active satellites out there right now, and you know, if you look at lots of pictures, you know, of whatever, I'm seeing a lot more satellites going through those pictures, and if we're talking about a doubling, yeah, that's really it's sort of a weird problem that, you know, I've been trying to think about. It's like, you know, how do you deal with that? You know, if you know, what goes through my head, right, is you know, you have like a photometer, right, which is extremely sensitive to light, right, and if you're observing some you know 23rd magnitude asteroid, right, and you're observing it, and of course you've got the gain like goosed way up, right, turned way up. If you get a bright, even a moderately bright satellite moving through that field of view, you're going to blow that thing. I mean, that thing's going to melt, right? So I'm trying to think about how, ways to mitigate that, and so far I've come up with absolutely nothing at all. It's a problem that it looks like we're probably going to have to deal with, because look, I mean, if some kind of entity, right, can offer gigabit Wi-Fi from anywhere on the planet for $50 a month, hey, I am signing up, right? I mean, that's a factor of 100 faster than what I've got now, and it's like, that's a no-brainer, right? So I mean, everybody is going to want this. Everybody. I mean, it's if they can pull it off, right, and make it work, which it sort of sounds. I heard something the other day. They had launched 2 of them with they launched 2 of them on a Falcon 9 a few months ago. I don't remember exactly when, as an experiment. And I just recently heard that experiment is going really, really well, right? I mean, it's successful. The satellites are working, whatever that means, right? So, I mean, it's sort of full speed ahead on this, and there is definitely a market for that, right? I mean, probably, I would say, and maybe you can correct me if I'm wrong, but half the planet, doesn't really have access to the internet, and may not even have computers, right? So, I mean, if half the planet would all of a sudden have access, right, to gigabit speeds, wow, that's a huge market. And like I said, me here, right, I am raising my hand. But the problem is, right, is that they're talking about something like 12,000 satellites. They're going to be in, I forget what kind of orbit they're called, but I think they're going to be like 1,000 kilometers up. So they're not going to be geostationary. So they're going to be moving, right? In all kinds of orbits, right? Because they want to be able to cover the whole planet. But with that many satellites, what are the chances of, even if you're just an astrophotographer, wanting to take a picture of Orion, right? Just having fun, with your camera and your scope, and want to get a nice shot of something, with twice as many satellites moving around up there, what are the chances of you getting a nice clean picture? It's probably, it's going to, that probability is going to double, right? So, yeah, I don't know. That's a problem that ground-based astronomers are going to have to deal with, right? Because it's probably going to happen. What do you guys think of that?
Well, I think it sounds like a traffic management nightmare if, they're going to have that many of them, and they're not going to be in some certain orbit where they can track them all easily if they're just kind of going around in different spots to cover the whole world. That could be an issue.
Yeah, I think, my guess is that, I mean, in terms of managing that kind of network, I mean, they're going to have to know where all these satellites are, because if they're moving, right, they're going to have to hand off signals, right? So at one time, um, I might be connected, to this one, and then as it moves, right, as it begins to set, I'm going to have to pick up another one, and so they're going to have to hand that off. So I think in terms of that network sort of being synced and knowing, where they are and all that, I think that's actually pretty easy, right? But I'm talking about a problem for ground-based astronomers who are sitting at their telescopes, right, collecting their data. They're sitting at Keck or Palomar or Kitt Peak, right, or any of them, Mauna Kea, and doing their observations, collecting their data, their spectra, their photometry, whatever it is. The last thing that you want, right, is some stupid satellite to go flying through the field of view and ruining your data, or even worse, blowing out your instrument because it's so bright. So yeah, I don't know how to mitigate that, because it sort of seems like that is going to be a thing that's going to be happening. So yeah, I don't know.
Well, how do they deal with that today?
Well, the number of sort of active satellites right now is something like 8 to 10,000, I think, right? And so, with this new constellation, they're basically talking about doubling the number of active satellites. I think the number of actual things up there, nuts and bolts and shoes and whatever. There's a lot more, right? But those are pretty small and pretty faint. So I'm sort of ignoring those. But like I said, I mean, you can go through photographs now, and a lot of the time, you will see a satellite track through it. And now it's one. Well, a couple years it's going to be two, and it's like, I mean, that's I don't know. That just seems to be a problem that I don't have a solution to. I mean, I don't think it's going to stop ground-based astronomy, but it's something that ground-based astronomers are going to have to start worrying about. It's like, you've got to think about your observing run, and you have to consider now the possibility of satellites moving through your field of view when you're trying to collect data. I guess the solution is to time things such that I guess that doesn't happen. But and that's an interesting opportunity.
Right here are actually going to be orbital satellites, and they just launched 2 as of now, right?
Yeah, I think they were doing an experiment with 2, just to sort of see how things work and everything else. I haven't heard any details, and I doubt that many.
And right now they're planning on launching 998 more, right?
No, I've heard numbers everything from about 8,000 to about 20,000. So yeah. Hey there, Daniel. Nice to see you in the chat.
Hey. What's up, Daniel?
So yeah, imagine, there's about 10,000 active ones now, adding 20,000 more, so 30,000. That's That's a lot. But it's an interesting opportunity, right? I mean, and I guess that's sort of how you have to see it. You know, it's a problem that has to be solved, and that's an opportunity. So, yeah, who knows? Who knows? Just some interesting things that go through my head during the day. So, and I was talking to somebody about it today, so I thought I brought it up again. You know, the other thing that I thought that we could do is, and in fact, I think before I do that, there was one thing that I sort of wanted to point out several days ago that I didn't. So yeah, let me bring it up now. So a few days ago, over on archive.org, they're started this huge number of papers talking about the science that is going to be able to be done with this new instrument called the Next Generation Very Large Array, the VLA, and they're calling it NGVLA. And there was just paper after paper after paper after paper, and I thought, wow, you know, what is this thing? And so what I thought I would do, well, there's actually a couple things. What they apparently did is they came out with a book, and every single chapter of that book they actually published over at archive.org. So you can either go there and get each one, or you can actually go to their site, which we're going to go to right now, and grab the actual book. It's let's see, do I have it here still? I thought I had it. I thought I had it here. Dun, 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 dun. Yeah. So it's 504 pages. It's a really that's a nice book, but it's all about the science that apparently is going to be done with this next generation VLA. So I thought what I would do, you know, because this live stream is about sharing and about, you know, sort of going on this journey together. So that's what I like to do. I sort of, you know, try to hold off looking at things and going to various sites and thinking about things until I'm here. So, you know, we can sort of share these things fresh, and you know, I just think that's the best kind of experience. I mean, if I were to come in here, you know, all prepared and everything else, then I would sort of sound like a, you know, some kind of a preacher or some kind of a teacher, and I am neither one. So no, I am on this journey with you, and so let's take a look at these things together for pretty much, you know, the first time. I sort of, you know, scan around a little bit and get an idea, but that's about as much as I like to do, because I like to come here and share it with all of you. So let's see. Let's go over to here. Let's go to their main site. So the main site is ngvla.nrao.edu. NRAO is the National Radio Astronomy Observatory. Let's see. I will post this in the chat. Dun, 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 just like that. So this hasn't been built yet, and I don't even know where. I don't even know where or anything else. Anyway, here's the book. So you can go grab the book At least when I grabbed it, it was free. So yeah, very, very cool. But what I noticed was that there's an FAQ. So I sort of thought that maybe we can just go through the FAQ and see what this is all about. Because I mean, FAQ is rightly named. So let's see. The next generation VLA is a future centimeter to millimeter wave interferometer that builds on the legacy of JVLA and ALMA. I'm not quite sure what JVLA is, huh? As the next major facility in ground-based U.S. radio astronomy, the NGVLA is optimized for observations at wavelengths between the superb performance of ALMA at sub-millimeter wavelengths and the future SKA1 mid at longer wavelengths. The NGVLA opens a new window on the universe through ultra-sensitive imaging of thermal line and continuum emission down to milli-arc-second resolution. Well, that's pretty amazing. That's as good as optical telescopes, as well as an unprecedented broadband continuum polarimetric imaging of non-thermal processes. The NGVLA will perform transformational science covering areas of terrestrial planet formation to the first generation of molecules. Okay, cool. Oh, where will the NGVLA be located? Let's look at that one. So that was sort of my next thing. So the NGVLA will be centered at the location of the VLA site. Okay, so also outside of Socorro, but it'll have additional long baseline stations spread over greater New Mexico, Texas, and Mexico. Wow, so that's kind of big. That's kind of big. Okay, so how big is one of the dishes, and how many of them are there going to be? Let's see.
These are like observatory, like radio telescopes style, or what?
Yeah, these are radio telescopes. If you've never seen the Very Large Array in New Mexico, let me show you that, Bobby, really quick. You'll probably recognize it as soon as you see it. It's pretty recognizable array, right? So here's the VLA in sort of a very, very small configuration. I think one of these arms, I think at its longest, is something like 7 kilometers or 17. I forget exactly. But yeah, so this is the current VLA just outside of Socorro, New Mexico. So yeah, it's just a bunch of radio dishes, and they're actually able to combine all the signals from these guys into one, and that makes for a more sensitive instrument, and also pretty high resolution, spatial resolution, right? They'll be able to, I'm not quite sure what the resolution of the VLA is, but I would say it's probably arc-second at least. Yeah.
We just can't just go into that facility and find out, huh?
No, you gotta, well, if you want to bust through a few gates and stuff, but, probably somebody won't like that. So, yeah, no, this is just like a regular observatory. So in order to to use these facilities, you have to write a proposal, right? And you have to explain.
Cosmic, speaking of like radio telescopes, I think either in Virginia or West Virginia, they got something called the radio blackouts area.
Mhm.
And there's like a city by that radio telescope. You can't have a cell phone. There's no Wi-Fi. There's no radio, none whatsoever. You can't have radio communications and stuff. And I think that's like a very good place to be.
Well, you're
It's
talking
a
about
national radio blackout area.
yeah, you're talking about the Green Bank antenna, which is this dude right here. So yeah, this the Green Bank telescope I think is part of the Deep Space Network, as well as I recall. Maybe not, but yeah, I mean it's a radio telescope, and you definitely do not want any RF in the air around this scope, right? This is a.
And thank goodness, like you got radio police in that area, good policing and stuff.
Yeah. Well, you know, it's not too hard to triangulate on any kind of transmission. So yeah, pretty easy to figure that out. So yeah, but it's a radio dark area. You know, the best, at least what I've heard, right? And there are plans to do this, but radio astronomers want to put their telescopes on the other side of the moon, right? So you know, one side of the moon always faces the Earth. I'm talking about the other side, because the other side of the moon is not going to see any RF from Earth, or just, I mean, yeah, I mean, I can't imagine, right? It's kind of interesting. The when the astronauts went around the moon, they experienced, you know, this radio quiet thing. But I heard something about them actually hearing something. Don't know anything about that though. But yeah, you know.
Let's go back to like whenever there was that day when NASA was faking the moon landings and stuff. And I was like, how in the heck they put like a camera on the moon, and next thing you know, there was like nobody there yet.
Well, those, yeah, I mean, those kinds of things can be done. Yeah, I don't necessarily see any kind of problem with that. Yeah, no problem. No problem. Anyway, radio astronomers would absolutely love to put radio telescopes on the other side of the moon, where you really do have, you know, radio quiet, right? Absolutely awesome. Anyway, so let's see here. So each dish is going to be 18 meters in size, diameter, right? And at least according to this, there's going to be 214 of them. Wow, that's a big number. I think the VLA has what, like 21 or something like that. So yeah, 214. That's an order of magnitude more. Wow. Let's see. Yeah, I still don't know what JVLA is. I need to find out what that is. Let's see. So, and an additional 19 6-meter dishes will make up for a short spacing array. Cool. Okay.
Yeah.
Kind of interesting. Okay, here's an interesting one, the frequency range. So they're going to be going from 1.2 to 116 gigahertz.
Oh, cover.
Okay, cool. Exploring an option for potential commensal observations at lower frequencies. That cover 5 to
Kind of
150.
interesting that they're covering the HF, BHF, and UHF.
Yeah, well, objects in the universe emit light at lots of wavelengths. So you can pretty much choose your wavelength, and you'll be able to do astronomy for sure. For sure. So yeah, these guys are into radio. So look at the universe in the radio. There's lots to be seen. That's kind of one of the interesting facets.
Now, when is this NGBOA going to be complete?
When? I don't know. Let's see if there's any. Okay, here. When will construction start, and when will operations start?
Let's start by construction start.
Okay, so construction, expect to enter the design phase in 2021, have a final design by 2023. Procurement and construction will commence in 2024 and be completed by 2034.
So let's find out when will the operations will start, shall we?
Well, it should be like 2034. Yeah, 2034. So that's a couple of days away.
So beta in 2028 and final in 2034. Kind of interesting.
Yeah.
Cosmic, the JVLA is just the longer name for the Very Large Array. That's the name of a guy, Carl G. Jansky.
Oh, Jansky. Okay.
Yeah, so they just named it after him.
Gotcha. Okay. Well, cool. All right. So that answers that one. Thank you. Okay. Here. What's it going to cost?
Okay. I like to look at the question. It says, will the NGBOA will have an open skies policy?
Oh, yeah. I mean, that's what this live stream is all about, right? So, yeah, let's definitely look at that next. So let's see. They've got a internal cost cap of 1.5 billion. Okay. That's a chunk. That is definitely a chunk. Looks like there's going to be partners, right? The U.S. is going to be a majority, but it looks like they're going to try to, spread the cost, which yeah, I mean, that's sort of typical. So yeah, that's a chunk, but yeah, they're trying to build 214 of these things. So yeah, that's.
Now, I want to look at the answer for the open skies.
Yeah. Let's take a look. So I assume what that means is the data going to be available, right? That's my guess. I don't know. Okay. So yes, we are planning to operate the NGVLA as an open skies. I'm not quite sure what an open skies observatory really is. I'm just guessing. Let's see if we can get
something like open base or something.
Let's see if
and Daniel Browning, they reckon it will pull down 6.4 terabytes of data a second. Well, even the Green Bay's got open skies.
6.4 terabytes a second? Ooh, Daniel, check your units. Maybe every day. Wow. Okay. Well, yeah, that's a very large that's a large amount of data. Ow, ow, ow. Let's
Yeah.
see. Open skies.
Oh,
Let's see what it
that's what they
says
got in
here.
some of the observatories.
Let's see what they
That's
say here.
interesting.
Open skies. Um,
So, um,
time for open sky science. This is not. This is not telling me anything about open sky policy. I've never heard of this open sky policy.
yeah, I wish they had Wikipedia. Maybe you can like probe Wikipedia in your Google search, and maybe that will be great.
Observatory open skies.
Yeah, try like adding Wikipedia and see if it's got something.
Let's see. I'll take your advice. Observatory. Let's do this.
Open.
Open skies is an international policy concept that calls for the liberalization of the rules and regulation. No, that's not that's not the kind of skies we're talking about. So yeah, open skies. Let's do.
It's the same thing. Okay.
Yeah. Huh.
Yeah. Well, I mean, if it's if
I'm
it's
not quite sure
open
what that means.
skies, um, it's I don't get this open skies thing here. I thought it was going to be like they're going to open base it and stuff.
Yeah, I sort of when I saw that, I sort of was like, okay, the data is going to be available, but now I'm not sure. I'm not sure. So, yeah, I don't know what an open skies policy is. Don't have a clue. Let's see what else.
Okay, check the chat because Uncle Bill Durham's posted something about open skies.
Uncle Bill is always on top of things. Let's see. The principle of open sky science is to maximize the scientific output of an instrument or facility through allowing any scientist in the world to apply for time on that instrument. Okay, well, Uncle Bill, how I interpret that, and I'm going to open your link while I sort of the way that I interpret that is when you build a facility, right? Usually the one footing the bill gets sort of first dibs, right? Or at least as much time as they want. And then if you have any other participants, they get a percentage of the time. So I guess what you're defining there as open skies is instead of sort of the partners who are building the facility and all that having sort of exclusive access, they're going to open it up to everybody. So okay, well, I mean that to a certain extent that sort of happens now, but if like 100% of the time is sort of available, to anybody who applies, then okay, that's an interesting concept. Yeah, I don't know, I mean, footing the bill for something and then not being able to use it. I don't know. So okay, so 6.4 terabytes a second is off of the public info
So there's
page.
like open skies. Is that like more of a law or something?
Yeah, okay. Let me try to explain it. Say, Bobby, that you and I and Tom all went in and built an observatory. Okay. Normally, what is then done is that, you know, I would have a third of the time, you would have a third of the time, and Tom would have a third of the time, right? Because I mean, we paid for it, right? I mean, you know, uh, um, um, it's you know, the funds, you know, we put in, and therefore, you know, it's sort of our thing. But I guess how I'm interpreting open skies is that that's not the case. We've decided amongst us three to sort of say, okay, you know, we'll build this observatory, but anybody can use it. So, yeah, okay, that's kind of an interesting idea. Yeah, I like it. What I wanted to do was go. Oh, yeah, I wanted to go back over here and see if we can. I want to, you know, I completely believe what you saw there, Daniel. But I would like to see that for myself. I'm just, you know, I'm a terrible skeptic. So.
Yeah, streaming 7.68 million Netflix movies per hour. That's gotta be strange.
Yeah,
I wonder if the modern internet can handle that.
well, that's an interesting. Because
here we are, we got like
question.
pretty much up to like 100 megabits or pretty much up to the gigabit, but terabits, I don't know.
Yeah. Okay. Well, here it is, right? With the NGVLA, we are creating new tools to process data in mind-boggling fast ways. Each of the 214 antennas will collect massive amounts of data and send it simultaneously to a super fast supercomputer called a correlator. So yeah, 6.4 terabytes of data per second. Okay. And so the correlator will have to deal with that. That is probably, well, yeah, wow. That's a big number.
6.4 terabytes per second. You can think about like 6.4 terabytes. You think that like even the largest file in the history of the internet, that it is just bam, done.
Exactly.
Because right now I can tell you how big is a 4K file. It's about 25 freaking gigs.
Yeah. Let's see. Here's a question here. Is the technology ready? So the NGVLA reference design includes an assessment of the technological readiness of each major element in the system, with the exception of the imaging pipeline and the data archive. The NGVLA systems could be built with 2018 technology. So there you go. With the exception of the imaging pipeline and the data archive. So, at least according to what they're saying here, our current technology cannot support that volume of data. So, yeah, they actually say here if Moore's law.
How do they get this terabit data or terabyte data?
Well, that's just a calculation, right? They actually talked about that, right? Let's go back. Let's go back to this. So let's look at this one more time, and then I want to show off the book a little bit too, and then we'll get out of here. Let's see, where was that? Yeah, so 214 antennas, 22,000 plus baseline combinations. So it's just, all these antennas are sending all this data, and they all have to be, cross-correlated, and that's what creates this huge amount of data, is all those combinations. So yeah, and at least according to their site, right? They don't have the technology yet in order to handle that. But they're hopeful.
And how did you get the bandwidth too?
Yeah. Well, bandwidth is probably a little bit easier because they'll be able to store all this data, and then they'll put it on a database, and then access to it after that is.
I was talking about the data cap, not the bandwidth.
Oh, okay. Yeah. Pretty amazing. So yeah. So here's the book. It's entitled Science with the Next Generation Very Large Array. And I was really interested and excited about all the science that can be done with radio astronomy. None of these things, I think, is really beyond the capabilities of what we have now. It's just, this next generation one will sort of be able to do it better, push the envelope a little bit, and all that. So here, let me zoom in, and we'll just go through this. High resolution imaging of comets, spacecraft telecommunications, resolved substructures in protoplanetary disks. So that's at least as the story goes, there are these disks of dust and gas around stars that are forming planets, and they're talking about being able to see structures in those disks, protoplanets, right? Disk winds and the evolution of planet-forming disks. SETI searches for evidence of intelligent life in the galaxy. That's kind of cool. Exospace weather. Prebiotic molecules. Prebiotic molecules. Wow. Does anybody know what that is? I don't know what those are.
Me neither. I still want to know what's a core right.
Yeah, but molecules. Most molecules do emit, mainly in the radio, submillimeter, that arena. So yeah, that's the best place to observe these anyway. Let's see, stellar activity on red giant and supergiant stars, classical novae, cool, evolved stars, complex organic molecules, detecting infall in high mass protostellar objects. star-forming filaments. So it's absolutely amazing what can be done. You know, the radio astronomy. Yeah, pretty awesome. H2 regions, radio jets, understanding massive star formation, protostellar multiplicity. Huh. Not quite sure what that even means. Protostellar disk formation, magnetic fields. Let's see, galaxy ecosystems. Radio continuum emission from galaxies. Radio recombination lines. How do cold gas outflows shape galaxies? Huh. Let's see. Astrometry and long baseline science. Yeah, that'll be nice. Galaxy formation and evolution. Molecular gas at high redshift. High redshift basically means, you know, long distance away. Continuum surveys. Carbon-2, singly ionized carbon, apparently emits at 158 microns. Okay, from galaxies extremely far away, Z greater than 10. That's very, very, very far away. Cold gas. Let's see. Carbon monoxide as a redshift beacon. Young radioactive galactic nuclei. Let's see, from megaparsecs to milliparsecs. Galaxy evolution and supermassive black holes. Okay. Supermassive black hole pairs and binaries. All right. Well, they're going out on the edge there a little bit.
So it's like going to plaid.
Yeah. Population of BHs. Ooh, I don't know what a BH is. Black hole? Yeah, I guess so. So revealing the galactic population of black holes using the next generation very large array. Okay. Pulsars in the galactic center. Huh, I didn't know that there were. Pulsar timing, cool. Gravitational lensing with carbon monoxide galaxies. Huh. So yeah, I think all these papers were published in these last few days over on Archive, but like I said, you know, they combined them all into one book here, and I'm always happy to see some pictures and stuff. So that's nice. Yeah, you know, us.
I think we can be seeing. I think we're going to be going to this book for days and stuff.
Oh yeah, you know, this is a book that you know, is definitely not light casual reading. This is yeah. I mean, you're going to dive into this and be into it for a while. This is
Hope you don't have a seizure or migraine or a Siamese attack while reading it.
I sure hope not. But it is radio astronomy, so you never know. All right, you guys. I'm noticing that it is 3:14 UTC. It's pi time, 3:14. So I think it's a good time to end this live stream for today. So just as a reminder, November 1st, 2nd, 3rd, and 4th. I think it's 4 days or 5 days. I forget exactly. There will be no live stream. I'm going to be out of town, which is
And I guess when we get back, it's Astronomy Day Live will be pretty much at 8 o'clock local time instead of 9 o'clock.
yeah. I think for most of you, there will be a time change, fall back. So yeah, our relative times are going to change, but the universal time is going to stay exactly the same. It's always 2 hours UTC. That makes it easy. There's just a single time, and yeah, as an exercise, you're going to have to figure out, right, what time it is for you locally. And that's a good way, to get into astronomy.
For me, you gotta subtract 6 hours.
You got to subtract 6. Yeah, I always have to subtract 7. So I'm always on Mountain Standard Time, which is 7 hours behind Universal Time. So yeah, always the same time here, which that's a nice thing. But if if people want to do daylight savings and all that, that's okay. You just have to keep track of it, right? And if you don't like it, well, try to get it ended. So I mean, it's not really necessary, but as long as everybody agrees, that's okay. No problem. All right. Well, I'm going to get out of here for now. So thanks for coming in again. Let's do this again tomorrow. Yeah.
Why not?
More astronomy. There's there's so much astronomy to talk about. I mean, it just goes on and on and on. The one thing that I didn't do today, which I'm going to try to do tomorrow, is I sort of wanted to dive into those Kuiper belt objects a little bit, and just sort of take a look at a few of them and see if there's anything interesting about them. So yeah, maybe we'll do that tomorrow or the next day. It's a very, very casual, fun thing here. So whatever happens, happens. But that's sort of what I'm planning on doing tomorrow. Is looking at those possible Kuiper belt objects that we might be able to visit in the next 25-ish or so years. All right. Well, with that, I'm going to get out of here. So have a great evening, a great day. Yeah. I will see you again tomorrow. All right. Take care, everybody. I will see you then. Bye.
Bye.
Later.